Hi everyone, my name is Cesar. I'm currently a PhD student from KTH Royal Institute of Technology in Sweden. Today I'm going to present our paper titled Coverage-Based Debloating for Java Bytecode. This work is co-authored by my colleagues Thomas Durio, Nicolas Agan, and my supervisor Benoit Baudry. This paper was published in 2022 in the journal Transactions on Software Engineering and Methodology. Let me show you the agenda for this presentation. First, I will give a little bit of background about software bloat, and I will present an illustrated example of the problem that we are trying to solve in this work. Then, I will give details about our tool called JDBL, which focuses on debloating Java bytecode using dynamic analysis and code coverage tools. Next, I will present our experiments and results when debloating libraries and assessing the impact of debloating on their clients. And finally, I will present our key conclusions and the future work. Software bloat is code that is packaged in an application but is actually not necessary to build and run the application. The existence of software bloat is a problem because it needlessly wastes developers' time and resources. For example, software bloat increases the size of software artifacts, creates maintenance issues, affects performance, and compromises security. Let me show you an example that illustrates the problem of software bloat. Consider a project P, and this project declares three direct dependencies, A, B, and C. But dependency A also have two dependencies, D and E. And also dependency C has another dependency F. In this case, D, E, and F are transitive dependencies of project P. Now, let's look at what is inside these software artifacts. Let's say that there are two components in P that use other components in dependencies A, D, and F. In this case, dependencies B, C, and E can be removed because they are actually not used by P. What you are seeing now is what we can get so far if we use state-of-the-art software debloating techniques that rely on static analysis. Now, let's suppose that there is an input that executes the path that goes from P to A and D. This makes part of the components in P as well as F unnecessary to satisfy the input. So we can remove them as well. And this is what we obtain when using software debloating techniques that rely on dynamic analysis. And then we can collect the used components, package them, and then build a single artifact called P' that only contains the necessary parts to successfully execute the application for the given input. Well, in this work, we have built such a tool that automatically transforms a project P into a debloated version that only contains the parts of P that are actually necessary to execute certain workload. Our tool is called JDBL, and it relies on existing code coverage tool to collect bytecode user information at runtime. JDBL is capable of removing methods, classes, and dependencies in Java projects that build with Maven. In essence, JDBL works in three phases. It receives as input a Java project and a workload that executes some part of the project. In the first phase, JDBL uses code coverage tools to collect bytecode usage information. Then, in the second phase, JDBL removes the unnecessary bytecode from the project and its dependencies. Finally, in the third phase, JDBL validates the debloating by executing the project against the same workload. If the result is as expected, then the project is packaged as a debloated jar file. We performed experiments to evaluate JDBL. For our first experiment, consider a project P, which is a popular Java library, let's say, that built successfully. Then we debloat P and obtain P prime. We check if JDBL produces a debloated jar. If that's the case, then we check if the jar preserves the original behavior using the same test suite. If all the tests pass, then we can say that the debloating was successful. We followed this approach and obtained a debloated jar for 302 libraries, and from these libraries, a total of 211 passed all the tests. This represents almost 70% of the libraries. This behavior assessment of coverage-based debloating demonstrates that JDBL preserves a large majority of the library's behavior, which is essential to meet the expectations of their clients. We measure the number of methods, classes, and dependencies removed in the successfully debloated libraries. JDBL removed 59% of methods, 60% of classes, and 20% of dependencies in our dataset. This result confirms the relevance of coverage-based debloating approach for reducing the unnecessary bytecode of Java projects while preserving the original correctness. We also focus on evaluating the impact of debloating on the libraries and clients that reuse the debloated libraries. For a client C that uses the original library P and builds successfully, we replace P by its debloated version, let's call it P prime, in order to investigate if the client still compiles and if the test suite still passes. If both are successful, then we can say that the client can use the debloated version of the library. Our results show that from a total of 938 clients, 96% of them successfully compile with a debloated library. This is the first empirical demonstration that debloating can preserve essential functionalities to successfully compile the clients of debloated libraries. Furthermore, from these clients, 81% of them pass all the tests. This means that JDBL preserves the behavior of most of the clients. We also found that 99% of the failures are due to a missing class or method, which can be easily located and fixed. This experiment shows that the risk of removing code in software libraries are limited for the clients. So, in conclusion, we presented our coverage-based debloating technique and used it to obtain 211 debloated libraries that preserve the original behavior, and these libraries are 68% smaller than the original. We also assessed the impact of debloating libraries with respect to the clients and showed that 81% of the clients are not affected by using a debloated library. Overall, our results provide evidence that coverage-based debloating is a promising technique that advances the state-of-the-art of Java bytecode debloating. In future work, we plan to use coverage-based debloating to debloat applications based on workloads collected in production environments. and we would like to extend our debloating technique to cover other part of the software stack. For example, to the Java runtime environment, program resources, or containerized applications. We invite you to read our paper for more details on this work, and feel free to get in contact if you have questions or comments. Thank you very much for watching.